So in the past, we've spoken about the relationship amongst elements within a particular group. And those are the columns going from top to bottom. So you have group 1, group 2, group 3, group 4, group 5, group 6, and group 7. And that tells you how many valence electrons you have of each element in a particular group. Group 1, you have 1 valence electron. Group 2, 2 valence electrons. We're going to jump over the transition metals because the number of valence electrons for each can vary. Although in group 3, which starts with boron, all these guys have 3 valence electrons. Group 4 has 4 valence electrons. Group 5, 5 valence electrons. Group 6, 6 valence electrons. Group 7, of course, they all have 7 valence electrons. And group 8 isn't considered to have any valence electrons since the octet is fulfilled. And of course, those outermost valence are very important since those are the guys that are going to react with valence electrons of other elements to create bonds and new compounds. So, what about the relationship of elements going from left to right? Well, these are called periods. And you have period 1, 2, 3, 4, 5, 6, and 7. And again, each of these are going to be in rows. You have rows of elements. First row, second row, third row, fourth row, and so on. That's really all a period is. But the information that's going to tell you is different than the valence electrons, but it's very important in terms of what's called electron configuration. And the electron surrounding a nucleus of a given element is said to be quantized. What does that mean? Well, quantized means that the electrons exist with only packets of energy. For example, if you have you have an atom here, there's the nucleus at the center, and you have an electron floating around. This electron is said to only have a set amount of energy before it gets, let's say, to the next energy level, where it has a new amount of energy. Okay, but it can't be in between. All right, that's a quantized amount. It's sort of like walking up a flight of stairs. You can go from one step to the next, but you can't really go in between steps. And what we can do using the periods is be able to tell exactly how much energy an electron has and where it's probably located around a nucleus of an atom or a group of electrons. So these are going to be located in these things called orbitals, which are spaces around the nucleus of an atom. All right. So the first thing you need to know is that there are energy levels. You might also see them as principal energy levels, depicted by the letter N. And these just sort of go along with the periods. So you have energy level 1, 2, 3, 4, 5, 6, and 7. Right. Now within those energy levels, you have these areas where electrons are located called orbitals. And there are the S, P, D, and F. And there are actually orbitals or a specific number of orbitals associated with each letter. So you're going to have a total of 1 s orbital in one energy level. You're going to have 3 p orbitals, 5 d's, and 7 f's. And within each one of those guys, you can only fit 2 electrons. All right. So Oh, man, spring's coming. Okay. For example, let's take hydrogen. Right? Now we know hydrogen has one electron because its atomic number is 1. And of course, atomic numbers tell us how many protons there are and the number of electrons, which is equivalent. So if we have just that one electron for hydrogen, it's in the first period here, and the first orbital to be filled in the first period or energy level is S, the electron configuration for hydrogen is going to be 1, S, and since there's only one electron going in there, it's going to be 1s1. All right? Let's take the next one. In the first period, we have helium. Right? Well, helium has 2 electrons. They're going to fill up the first energy level and the first orbital within that first energy level. Except this time it's going to be 1s2 since there are 2 electrons fitting in there. All right. Now we need to go to the second row or second period. So that's lithium. Let's try to figure out the electron configuration or the placement of electrons of those 3 for lithium. Well, you know that the first orbital of the first energy level is going to be filled. So we'll put 1s2. Now it's moving down to the second energy level. So it's going to be 2. And again, there's going to be an s orbital that begins, or rather it's the first orbital of a particular energy level to start being filled. So it's 2s1. There are your 3 electrons. So the electron configuration for lithium is 1s2, 2s1. Next element is going to contain 4 electrons. That's beryllium. And beryllium is going to be, well, we're going to fill up the 1s2. And look at what we're doing now. We're filling up the 2s2. Since you can fit 2 electrons on each orbital, the electron configuration for beryllium is going to be 1s2, 2s2. All right. We're going to jump over to the next element in the second period, which is boron. And boron has 5 electrons, since its atomic number is 5. It's going to fill up the 1s2 first. It's going to fill up the 2s2. But now, something's going to happen. In the second energy level, we're going to begin to start filling up p's. So the electron configuration for boron is going to be 1s2, 2s2, and now it's 2p1. Right? And the reason is because once you start getting to boron, you've already filled up what are called the s blocks, and now you're starting to fill up all the p block or p orbitals. All right? And if you follow along with the periodic table, it's organized in such a way so that you can easily determine which energy level and which orbital a subsequent electron for a subsequent element is going. For example, carbon has 1 more electron than boron. So now we're going to fill up the 1s2. We're going to fill up the 2s2. We're going to fill the 2p1, and now we're going to 2p2. All right. And it continues from there to nitrogen, which is going to be 1s2, 2s2, 2p3. All right? And the reason why you're going to continue with 2p3 is because each one of these orbitals can fit 2 electrons. So in total, the s's, you're going to be able to fit 2 electrons. For the p's, you're going to be able to fit 6 electrons. For the d's, you're going to be able to fit 10 electrons. And for the F's, you're going to be able to fit 14 electrons. All right? Since in each energy level, there's 1 S, 3 P's, 5 D's, and 7 F's. Or actually, I should say, the potential exists for an energy level to have all of these. And the number of energy levels are that you have are going to increase because you have more electrons to fit in there. Right? So let's jump over to, let's say neon. Neon is going to be 1s2, 2s2, 2p6. Because now everything in the p block is filled, and the p's can fit 6 electrons. So you started off with 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And with that, you can then predict what sodium is going to be because it's starting in group, or actually period 3. And sodium is going to contain 1s2, 2s2, 2p6, and now there are no 2p7s. I mean, you just have to look at the periodic table, and you'll be able to know that the next one has to be 3s1, since it's going back to the s block now. Then you have magnesium. It's going to be the same thing, except now it's going to be 3s2, and so on. A shorthand way to write this could be for magnesium. It's also going to equal, you might see it written like neon and then 3s2. Because rather than write out 1s2, 2s2, 2p6 all the time, well, if we just write down neon in brackets for this group 8, it's going to tell us, okay, well, it's just like neon. All of these orbitals are filled just in comparison or exactly like neon. But now we're just going to add 3s2 to that, and that's magnesium. See? And of course, aluminum, you're going to get to 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Then it's going to go for potassium, 4s1, 4s2, and so on. All right. So let's do the electron configuration for calcium. So hopefully I got room on the bottom here. Calcium is going to be argon, put in brackets, or all of the electrons of all of the inside all of the orbitals, inside all of the energy levels of argon. And then it's going to go to 4s1, 4s2. All right. But now let's go to, let's say, iron. What's that going to be? Well, here's where it starts to get a little bit tricky. Because iron is now argon, or the electron configuration of argon, and the 4s2 is going to be filled. But here's where we start filling up the Ds. And that's why these are called the D block transition metals. So how many do you have? Well, you have D1, D2, D3, D4, D5, D6. So you have 6 electrons inside those d orbitals. But the first d shell to be filled is after 4s, and it's the third energy level d. All right, so this is actually 3d. All the way across. And then what happens when you get to, let's say, bromine? What's the electron configuration? Well, we have to go back to the most recent group 8, noble gas, which is, again, argon. And now it's 4s2, 1, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which makes sense because remember when we said that there are 5 d orbitals and we can fit 2 in each, that's 10 electrons. And now it goes back to 4p. So it goes back to 4, and then after S, 3d, 4p1, 4p2, 4p3, 4p4, 4p5 for bromine. So again, those transition metals always make everything a little bit more tricky, where you have to do some thinking. But if you remember that when you go across the 4th period, that when you get to the D's is 1 energy level down, you won't make a mistake. And then when you get over to the P's, or the P block, it just goes back to the 4th energy level. Right? More, we'll do, let's say, in the 5th period, we'll do 10. SN. So electron configuration is going to be the previous noble gas, Kr. The 4s2 from the S block is going to be filled. So actually, I'm sorry, 5 S2, it's in the 5th period. So let's try another one. Let's try tin. Tin. We'll look at the previous noble gas, which is Kr, and then it's in the 5th period, so that's 5s2. It's going to be filled first. Remember, these are the S's, these are the D's, and these are the P's. And then it's going to go to 4d10. Remember, you can fit 10 inside the D, and it's always 1 less than whatever period you're in. So it's D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Then it's going to go back to 5p1, 5p2. All right. Now, if we go to something in the 6th period, something happens right here, where it jumps to the F block. It's down here. And the F is actually going to be incorporate itself into the electron configuration, just like the D did, but now it's going to be 2 energy levels less than whichever one you're in. For example, if you have something like let's say tungsten W, right? Well, you can look at the previous noble gas, xenon, and it's going to be 6s1, 6s2, and then it's going to start filling the F's, right? So it fills up all these guys down here. It's going to be 4f14. All right, so we're jumping to this row, and then we're going back to the D's. It's going to be 5d1, 5d2, 5d3, 5d4. All right. And for, let's say, in the 7th period, let's try another one. Let's try BH, which is going to be Rn, 7s2, 5f14, because now we jump down to this. F block over here. And it's going to go to 61, 62, 63, 64, 65. And that's probably as tough as you're going to get. All right? And that's how you incorporate the D's and the F's into the S and the P's. To sum up everything in terms of filling orbitals, and the periods 1 through 7, it's going to go like this: 1, 2, 3, 4, 5, 6, 7. And in the first period, it's just going to be 1s2. In the second period, it's going to be 2s2, 2p6. In the third period, it's going to be 3s2, 3p6. In the fourth, it's going to be 4s2. Going to get to those D block, that D block now, 3d10, 4p6. In the fifth, it's 5s2, 4d10, 5p6. In the sixth, it's going to be 6s2. Then it's going to jump to the F's. You can fit 14 of those guys in there. 4f14. Again, we're right here now. 5d10. So then it goes here. And then 6p6, which would be these guys here. And finally, for the seventh period, 7s2, 5f14, 6d10, and 7p6. And that would be potentially the last one for the last period, which hasn't been discovered yet. So that would be the order of filling as you go along, and that's going to help you write each individual electron configuration for each element.